Hello everyone, welcome back to the channel. Today we are going to tackle a foundational problem on Leetcode, same tree, problem number 100. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given roots of two binary trees, P and Q, and we have to write a function to check if they are same or not. Two binary trees are considered the same if they are structurally identical and the nodes have the same value. For example, here in example 1, both the trees have the same structure and same values at each position. The roots are both 1, the left children are both 2, and the right children are both 3. So these trees are identical and hence we will return true. However, in example 2, the structures are different. Even though the root values match, the root of the first tree has left child, but the root of the right tree has right child. Hence, even though the node values are same, the structural mismatch means that these trees are not identical. So we will return false. And finally, in example 3, the structure is same. Both roots have a left and right child. However, the values don't match. The first tree has a left child with value 2 and a right child with value 1, while the second tree has a reverse. So because of this, the values corresponding to nodes are not equal and hence the trees are not identical. So we return false. So how do we want to tackle this? Since it's a tree problem, we can immediately think of applying depth first search aka DFS or breadth first search aka BFS. While both can work, a recursive DFS is the most straightforward and intuitive path where we simply compare trees piece by piece, starting from the root node. And here the roots are equal because both of them have value equal to 1. So they match. And this seems like a necessary first step because if they didn't match, we could stop here right away and say that the trees are not identical and return false. However, here, since the roots are good, we can't stop yet. We also have to ensure that their entire subtrees match. So we recursively apply the same logic to its children and compare the left subtrees in both the trees and right subtrees. And if the root nodes match and the left and right subtrees in both the trees match, then only we can say that the trees are identical. So now let's move to the left subtrees of both trees. The left child in both trees is a node with value 2, which results in a match again. Now, what about the children of these nodes? Well, the left child of node 2 in tree P is empty or null, and the corresponding node in tree Q is also null. And when they are both null, they are identical for this path. So this gives us a crucial stopping condition or a base case. So if we are comparing two null nodes, they are the same and hence we can return true for this comparison. But what if one of them isn't null? For example, we had node 4 here as a left child while the corresponding node in tree Q is null. In this case, the structures would be different. So this gives us our second base case, which is if one node is null but the other isn't, then the trees are not identical due to structural mismatch and hence we will return false. But here they do match as both the left children of node 2 in both the trees are null. So we are done here and we do the same for the right children and they are also both null, which is another match. And since both the checks on the children of node 2 passed, we have successfully verified that the subtrees rooted at node 2 are identical. And so now we backtrack and do the same for the right side, and the right child of root is 3 in both trees and they match, and the left and right children of node 3 are both null, so they also match, and hence the right subtree is identical as well. And now that we have visited every node and every single comparison has passed, we can finally conclude that these two trees are identical. So to summarize, our recursive logic relies on three critical checks or base cases when comparing the two nodes in both the trees. If they both are null, we return true. But if one is null but other is not, or if their values are different, then in this case we return false. But if nodes pass these checks and then their left and right subtrees pass these checks as well, then only the trees are identical. Now the time complexity of this approach is O of n, where n is sum of all the nodes in tree P and tree Q. Because in the worst case, if the trees are identical, we have to visit every node in the trees at least once. So the time complexity is directly proportional to number of nodes in both the trees. And the space complexity will be O of h, where h is the height of the tree. As we are using the recursive approach, the depth of the call stack is proportional to the tree's height. For a balanced tree, the height is log of n, making our space complexity O of log n. But for the completely unbalanced or skewed tree, the height becomes n, leading to a worst case space complexity of O of n. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on the left and Python on right. We first handle our main base case. If both nodes P and Q are null, it means we have reached the end of the branch on both trees simultaneously, and they are structurally identical at this point, so we return true. Next, we check all the reasons the trees might not be the same, where we check if either of the node is null. For example, if P is null while Q is not, or if Q is null but P is not, or both the nodes exist but they have different values. If any of these conditions are true, we have a mismatch and we immediately return false. But if we have gotten past the previous checks, it means the current nodes are valid and their values are equal, and we have to ensure that the rest of the tree follows suit. So we recursively call and compare the left subtrees and the right subtrees. And if both the calls return true, that means the trees are identical and hence we will return true. But if either side returns false, the whole expression becomes false. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.